Okay, well, good morning, everyone. This is the second talk by Michael Perryman. Dr. Perryman was introduced in the previous talk by Pedro Amado, and just let me say a few words about Michael, and in particular, I think the IAA is very kind to have Michael here with us, because Michael is part of our Scientific International Advisory Committee, so he's extending a visit here with us at the IAA. And, but not only because of that, he has been very close to the Institute, in particular very recently in relation to the Carmenes instrument, and in the last phases, the very important phases of Carmenes, he has been one of the pillars for the development of the instrument, and I would say his help was fundamental for the instrument to be finished on time, and is now, as you know, at the Observatory taking data very successfully. Another point which I would like just to mention here today is that I think he's a balance. It's a very, very it's one of these astronomers that I read from your CV that you very early in your life, with I think 26 or something like that, you take this responsibility, this high responsibility with the mission, and this is very, very important for the young people to believe that this is a question. It's not a question of age, it's a question of, of course, personality, but also a very, very strong background. And the last point I want to mention in relation with the talk today, ELISA mission, is why is Michael here speaking about ELISA mission. He just come to me. He was, because somebody very important asked him, is really possible from space, it's really possible to measure gravitational waves? So this is a crazy idea. Is that just a crazy idea, or is it possible? So he has to come back to the ESA after 2009, two years ago, and to produce ESA, to give ESA an answer to this question. And this question, of course, is positive, and that is very kind for all of us. So we are eager to see this mission working. Thank you.
Thank you very much. Is anyone involved in gravitational wave research? Is anyone planning to get involved in ELISA? So one person here. All right. So perhaps many of you will know about the plans that exist now for a mission in space to detect gravitational waves. It's been known as ELISA for a long time. It's been studied for a long time. And 3 years ago, it was finally given basically an approval. It will go ahead, it is happening, and the idea is it will be launched in 2034. 2034 is still 17 years away. It seems a long time. There's a lot to do. As you know, people who were at my last lecture last week know that I spent 29 years working on space astrometry, Hipparcos and Gaia. These are very, very challenging missions. They don't seem necessarily very closely related to ELISA, or detecting gravitational waves, but as you will see, the two have quite a lot in common, and the technical complexities have quite a lot in common. And a couple of years ago, the Director of Science of ESA, Alvaro Jimenez, asked me to chair a committee, international committee, European, American scientists, to report back to him with the basic question, is ELISA technically feasible? Is it a mission that we can do? Now, the reason why this is such an important question, if you look at I will describe in more detail, but if you look at the basic idea underpinning ELISA, it is to have 3 satellites in a triangular configuration separated by about 1 million kilometers, and one has to measure the separation between them with an accuracy of about 10 picometers. So if you look at this basic question, you say, is it possible? Can it really be done? And that is the goal of this committee, and that's what I will talk to you about today. Let me admit, firstly, I know essentially nothing about gravitational waves from a theoretical point of view. I have never investigated the basic equations that describe the general relativistic curvature of space-time and the propagation of gravitational waves, but one can pick up very, very simply the basic concepts of this, and that is that massive bodies in orbit around each other, so we're talking here things of the mass of the sun or more, orbiting each other are losing energy by the emission of gravitational waves, and these gravitational waves spread out from these orbiting bodies, and the effects then ripple across the universe, propagating at the speed of light, and generating a perturbation in the metric of space-time, which we can think of as an oscillation in separation. If I've got two objects separated like this, space-time is fluctuating and the separation between these changes. So it's a prediction of general relativity. I guess until 18 months ago, with the first detections of gravitational waves, there were some people who were still a little bit nervous about whether this prediction of general relativity was true or not, or whether you can decouple it and actually measure it in the way proposed. But I think the first detection of LIGO in September 2015 is indeed a full confirmation that this is real. Now, before I talk more about the technology and exactly what ELISA will do, let us look at this oscillation of space, this fluctuation in the fabric of space, here on the ordinate, and here is the frequency. So 1 hertz, 100 hertz, 10 to the 4 hertz. So going to higher frequency in this direction, lower frequency in this direction, and it plots the kind of effects that one can hope to see on the ground. So this is the frequency range that LIGO on the ground is sensitive to, and this is the frequency range that we're sensitive to with interferometers from space. You can think of this simply in terms of the baselines of the instrument. LIGO is whatever it is, of the order of a kilometer baseline. ELISA from space is of the order of 1 million kilometer baseline, and you're sensitive then to the propagation of these gravitational waves in this way. I'll say a little bit more about the kind of sources that appear in this wavelength region, and the kind of sources that appear in this wavelength region. I'm not going to talk to you about the technology of ground-based gravitational wave detection, which I think in some ways is even more complex than the problem of doing it from space. And the reason one is limited on the ground is that here you are just looking at fairly high frequency signals, and if you try and measure the low frequency structure from the ground, you're influenced by things like seismic properties of the Earth and problems like that, gravitational gradients of the mirrors and so on, which prevent you on the ground from going to these lower frequencies. There's a lot of information in the astrophysical information in the frequency band of ground-based detectors. There's even more in the frequency band of space detectors, as we'll see. Now, again, one can be, starting off with the equations of general relativity, you can be fairly confident that if you've got something like a compact white dwarf binary in the galaxy, or a coalescing black hole in the galaxy, you can go through and calculate what kind of what is called the strain, which is the amount, the fractional extent by which space-time is moving because of the gravitational waves. The kind of strains that you're looking at here is of the order of 10 to the minus 20, 10 to the minus 16 for very bright sources. So this means again that if you can measure over very long baselines, you only have to measure smaller separations for longer baselines because of this fractional strain. So since 2015, LIGO has been operating on the ground. It's believed to have something like a 70 megaparsec horizon for binary neutron stars. And the various runs that have been running, and they stopped to upgrade the instrument, and the idea is that by 2021, advanced LIGO will reach its ultimate design sensitivity and be sensitive to more and more sources. So let's have a look, go through this in a little bit more detail. And if I plot on this plot of what is called the strain, so you divide the amount by which space-time is fluctuating by the baseline, and that gives you the strain, and here's the frequency. And in these instrument designs, you end up with a sort of sensitivity curve which looks like this. This is dependent on I'm going to describe a little bit more how these instruments operates, but we have some test masses which are flying in space, and these are shielded, these test masses are shielded from external sources of perturbations and noise, and at a certain arm length separation of this interferometer, if you can control the noise levels down to a certain level, you come down here. This is this arm of the response curve is the effect of the acceleration noise at lower frequencies, and this response arm rising at higher frequencies is just due to the fact that for any given separation of your satellites, as you go to higher and higher frequencies, there are more wavelengths of your gravitational radiation within a specific arm length. So you don't increase your sensitivity by going to longer and longer arm lengths for these high frequency gravitational waves. Now I want to focus a little bit more today on some of the technologies or the ultimate feasibility, but let me just go quickly through some of the physical classes of object which are believed to be detectable with LISA. And there are three main classes, plus a lot of more hypothetical things like the fabric of space-time in the early universe. But the first of these is compact white dwarf binaries, so something like a stellar mass binary in quite compact configurations. One knows that some of these we know about. They're estimated to be something like 10 million in the galaxy. They are monochromatic sources, or expected to be monochromatic. In other words, they're rotating, they're orbiting each other, and they're not strongly changing these orbital properties with time. So they're sending out gravitational waves at a particular frequency. And if you plot then where these will sit on this kind of sensitivity curve, you will see that individual resolved sources, that these are simulated in the galaxy, and then there are a few shown here with circles that are already known. These are known to exist in particular binary configurations, and these are referred to verification binaries because we know what they are, we know where they'll be, and you know what you expect to see. there's a sort of background signal of unresolved binaries, but let me skip over that for the moment. But if you construct something like a ELISA type instrument in the way that I will describe in a little while, you end up with a sensitivity curve like this, looks something like this, and several thousand of these white dwarf binaries that should be detectable above this signal to noise. The next class of target are what are called extreme mass ratio inspirals, and this is when you have a very massive object orbited by a less massive object, and the less massive object is spiraling into the gravitational field of the more massive object. And these extreme mass, the previous class I showed you, the compact white dwarf binaries, these are roughly equal masses. The extreme mass ratio inspirals are something like a black hole, say something like a one solar mass star or neutron star orbiting something like a 10 to the fourth mass black hole. And the idea is that towards the end of their inspiraling, they will be coming closer and closer and closer, and then they eventually plunge and collapse and coalesce. Now again, modelling these sources is not my area of expertise, and for most of you it's not your area of expertise, but you might imagine that if you can hypothesize the existence of these things, then you can sort of calculate, model what the gravitational wave will look like. And this depends on things like the eccentricity, it depends on the orientation, it depends on the mass ratio, and it depends on how far you are into the inspiraling. The end result of this is that there are likely to be a whole array of very complex waveforms that arise because of these. And people are fairly confident from a theoretical point of view that these exist. And they sit quite low down here on this, and as time progresses they move across the frequency response curve as they spiral in. The third type of target, and again, I think if you're not working in this area, this sounds a little bit, it's been a few years since I sort of looked into the more cosmological or what's going on in the centre of galaxies, but I think there is good, yes?
Is it right that these more massive, more extreme objects are less detectable than the white dwarf binaries?
No, I was just showing you that they are. I mean, some of the white dwarf binaries. I'm not sure exactly how many of these that are predicted, but they come. Depending on the mass ratio and how close they are, they are slightly, I suppose, lower down. But we'll see. I put these all together in just one moment. Let's come back to that. The third class I want to talk about are the massive black hole binaries, and I think any of you working in the areas of sort of galactic structure or evolution of the formation and structural formation in the universe will know that there are predicted, or observationally one knows that there are these massive black hole binaries within galaxies, and they are believed, if you look at this right hand diagram here, this is supposed to be cosmological time, running back to very high redshifts. The idea is that structure in the galaxy partly originated through the formation, the coalescence of these massive black holes as time proceeded. And this is exactly what's been seen with advanced LIGO. It's looking back and seeing 230 solar mass black holes coalescing at a redshift of, I don't remember what they were, redshift of 3 or so, I believe. So those people that know this area, I think, are pretty confident that these are going to exist, that you're going to see them, that there's lots of them going on if you can look back far enough, and ELISA will be able to look back to something like a redshift of 10, and what this means is you're looking out into the universe, and on one particular day you'll see these supermassive black holes coalescing as they coalesce back at a redshift of 3, 5 or whatever, and you'll see a whole succession of these, perhaps 100 or a few hundred of them during the ELISA lifetime, and it will tell you information about how the merger history of the universe operated. And these things are, as they coalesce, and this is again exactly what was seen with the advanced LIGO first detection, what you see is this very rapid inspiraling, plunging, merging, and what is called ring down, which is occurring within a fraction of a second when these black holes finally coalesce. I mean, the physics is quite astonishing, isn't it? I mean, even with the advanced LIGO detection, you're looking at a 30 solar mass black hole coalescing with another 30 solar mass black hole, and 5 solar masses of 5 solar masses of mass is vaporized and lost in that energetic process. So again, the people involved in this are busy calculating what are the kind of signals that would come from these mergers, and we'll see, I'll come back and show you the advanced LIGO signal later on. But here we're looking, you can be looking at, typically this is 0 to 0.3 of a second, or 0 to 0.01 of a second, a tenth of a second, and you're seeing these very complex inspiraling merging in these final second or so of the collapse of these two black holes. So that's what these will look like, the supermassive black holes. And I suppose the extreme mass ratio in spirals, that they're low down compared to some of these more prominent examples of the supermassive black hole binary. So here you've got what happens if a 10 to the 7, a 10 million solar mass, 10 million solar mass black hole merger. And this is where the signal would be 1 month before the final coalescence, 1 week, 1 day, 1 hour, and then the final plunging and ring down as the systems converge. And similarly, a 10 to the 6, 10 to the 6 solar mass, 10 to the 5, 10 to the 5 solar mass, you can plot where they will appear in this response curve and how they will evolve as they coalesce. If we put that all together, if you can design something like ELISA, then within the detectability regime, you will be able to see things like the compact white dwarf binaries, many thousands of them, these extreme mass ratio in-spiral sources, I think several hundred of them, and several hundred perhaps of the black hole binaries. Now again, I won't be going into this, but when you look into the physics of it, ELISA is not just about detecting these gravitational waves. The question is not simply, can we detect them or not detect them? Are they there or not there? It's actually looking at the physical properties of them and the properties of general relativity in these high mass regimes. What are the properties of the black holes, and so on and so on. There's an important property of gravitational waves called polarization, in analogy to optical polarization or electromagnetic radiation. And I don't understand this, so I'm not going to take you through it, except to say that if you have more than one of these baselines, you can hope to measure the two polarization states at the same time, and that gives you information more on the physical properties of the system. I'll come back and mention polarization. All I wanted to admit is that I don't understand the physics underlying polarization of gravitational waves, so I don't want any questions on that at the end of my talk. That's my humour. All right, measurement principle. The idea is the underlying ELISA is really very, very simple. You're going to have they choose cubes, 2 small cubes. They're choosing gold, platinum, for various reasons that we don't need to go into. Pathfinder, ELISA Pathfinder was about 5 centimeters, the cubes were about 5 centimeters. And what you're going to do is bounce laser light backwards and forwards between them, and we're going to measure the path length difference between them. Now, there's two things then involved in that. One is, well, how do we make those path length measurements? Well, it's basically laser interferometry, and this is a standard technique in laboratories, and the application to how you do that on space is considered to be fairly straightforward, with one or two exceptions. But the other thing we need to do is to protect these cubes, these test masses, from other sources of perturbation that are going to hit them in the space environment. So things like particle radiation from the sun, cosmic radiation, gravitational perturbations from the satellite itself, and so on. So I'm going to ask you to imagine somehow surrounding these test masses with some kind of protective shield, which we then use to allow the test masses, what we call free-flying, drag-free operation, shielding them from all the external perturbations that can buffet them, move them around. And then all you're left with is the component that is due to the passage of gravitational waves passing across the test masses. So that's the idea. This is what was done in ELISA Pathfinder. They were separated, these test masses were separated by about 38 centimeters, and the path length separation in ELISA Pathfinder was measured to of the order of 10 picometers. Now, when I'll show you a little bit the kind of conceptual diagram for how the laser interferometry is done, but again, for those of you, there are probably some people in the room that know more on laser interferometry. In the lab, you can measure separations between mirrors down to a few femtometers. Is that right? A few 10 femtometers?
I find it still unbelievable.
Well, it's using just path interferometry, and this I'm not talking about in the gravitational wave community. I'm talking about groups that work on laser interferometry for whatever purpose, and this is done down to the levels of around 10 femtometers. So something of order 1,000 times better than you need to do with ELISA or ELISA Pathfinder. Now, again, the important thing conceptually in this is if you can imagine, let's assume, for example, you can sit in a laboratory and measure, you have two mirrors separated by a meter or whatever, and you use interference to measure the separation between them. If you can do this to, say, 10 femtometers, it doesn't matter if I move those mirrors apart by 10 meters, I'm still measuring, a 10 femtometer separation introduces a path length and an interference effect in that light that's quite independent of the baseline over which you're measuring. So if I now move these mirrors or reflecting surfaces by a kilometer or 1,000,000 kilometers or 5 million kilometers, it doesn't alter the fundamental problem of measuring a path length separation. That 10 picometers is still whatever fraction of a wavelength that you're measuring interferometrically. It's quite independent of the path over which you're measuring it. Now, of course, there's a practical question. How do you do that? How do you get a laser big enough to shine over a distance of 1,000,000 kilometers? But this is more in the technical implementation than the conceptual difficulty. So I think I'll say a little bit more about that, but I think the first thing to grasp is if you believe this 10 picometer separation between mirrors can be done, or test particles can be done in the lab, and it can certainly be done at the level of 10 femtometers, then there's no reason why you shouldn't be able to do this in your spacecraft. And as I say, the next step is to have a drag-free, some kind of shielding from the external forces and so on, that takes away the sensitivity of these test masses to other perturbing forces. And the way that is done, again, just conceptually, and it's been done in ELISA Pathfinder now, and actually it's been done in something like 10 satellite missions since the 1970s. I didn't know this until I started looking into it, there's several space missions that have actually incorporated this. So things like GRACE, Microscope, the French fundamental physics mission launched last year, Gravity Probe A, and so on. Now, they've not done this to the precision needed for ELISA, but it's been done. And the idea, again, is that you have your test mass, this cube, inside a sort of cage, inside a kind of box, and what you're doing continuously is then sensing the separation between the cube and your cage. Now, I don't know how I can, whether I can, the concept is sort of fairly simple. You've got this free-flying test mass, you've got a cage around it. I'm going to measure somehow the separation between the cage, this is done electrostatically, between the cage and the test mass. And as the satellite is flying through space, if you sense that this test mass is moving closer to one of the edges of your surrounding cage, you fire the thrusters on the satellite to move the cage back in the opposite direction. All right? So the idea is simply to, your satellite is taking all the external forces hitting it, and you're using the sensing of this external cage and the test mass to continuously adjust the attitude of the satellite so that the cage doesn't interact with the test mass. And this needs to be done with a precision of a few micronewtons. So these thrusters have to operate with a precision of a few micronewtons, and this is exactly the thrusters that we use for Gaia to control the Gaia spin rate. So again, we know that this kind of attitude control can be done with the technology that one has at the moment, and this whole caging mechanism was demonstrated precisely with ELISA Pathfinder. ELISA Pathfinder uses exactly this technology to maintain this, what is called drag-free control of the test mass. All right? Now, I hope at this point, I'm going to say a little bit more about how this is done in practice, but I hope at this point you've got a conceptual idea. We know from a theoretical point that these gravitational waves are going to generate perturbations in space-time of the order of hundreds or thousands of picometers. We want to be able to measure that to about 10 picometers. We're going to do that by having laser interferometry operating between two test masses set out over about 1 million kilometers that allows us to measure these kind of strains and then surround it in this drag-free attitude control system so that the only things affecting the test masses are the gravitational waves. You had a question?
Yeah, I was just thinking, you're just trying to maintain this cube to be constant in space.
Yeah. Again, if you can look at it the following way, if you could somehow have these two test masses, we're just going to shine the laser light, but the reason that you've got a test mass at all is just to give you something which is affected by the gravitational waves. You can think of it as shining the laser light between the surfaces of those cubes, and if you could simply organize it so that those test masses are not perturbed by any other forces, then you're home and dry. So let's have a look now, just quickly, the history of ELISA, because it goes back a long time. It goes back to 1985, where the first concept came up, and the first concept, so this is 32 years ago. And even at that time, the first concept called for 3 spacecraft and 2 arms separated by 120 degrees. In 1993, I think this was this was a US proposal, and here's the first European proposal, 1993. So almost 25 years ago now, it was proposed for medium mission within the Horizon 2000 program by Carsten Dansman, the German PI, who is still the PI 28 years later. In 1997, it was recommended that in ESA that this program is done in collaboration with NASA. Over the next few years, there were various assessment exercises. In 2011, so just 6 years ago, basically NASA pulled out of the collaboration between the ESA-NASA collaboration, and it was left then, for whatever reason, NASA decided they weren't going to fund this, they didn't want to proceed with it, they didn't have the money, and therefore it was left as a purely European mission. And at this stage, it was renamed NGO or ELISA, New Gravitational Wave Observatory, and there was quite a lot of de-scoping done with that. In 2013, ESA Science Program Committee selected as the L2, so the large mission number 2, it selected the X-ray mission Athena Plus, and it selected L3 as the gravitational wave mission for 2034 launch. 2034 being dictated by the financial envelope of the ESA science program, not the kind of technology limit of this. So this committee was set up to look into the question about, is it feasible? Is laser interferometry still the best approach? I won't say more about that. We looked into atom interferometry and came back with recommending laser interferometry. And how does one organize the technical development in order to ensure this kind of cost and risk? So we reported back in the middle of last year, and the final report's available. And there was a committee of about 10 people, half of them from the US and half of them from Europe, including people involved in ELISA Pathfinder. Now, I'm not going to say too much about the technology, but I think a few pointers just to show you, again, the essence of it. First of all, imagine two arms, a two-arm interferometer. So just looking at a single baseline measurement. And here you've got one spacecraft, and here you've got another spacecraft, and we're going to separate these spacecraft by about 1 million kilometers. Then what you have is our test mass. Here's one test mass on one, proof mass on one satellite, and here's the one on the other. And it's put in this kind of caging mechanism. And we're going to bounce a laser beam. Here's the source of the laser light, reflector, bounce it off here, send it over here, recombine them, which I'll say a little bit more about, and measure the path length separation between them. That's the principle. The laser light from this satellite is sent down here. It spreads out, it's picked up by a telescope, and goes through the detection process in the other satellite. When you look into the optical arrangement in ELISA, the optical benches start looking very complicated, but in fact, all part of this is just due to convenience. It turns out to be more simple to you have an optical bench on one satellite, an optical bench on another satellite, and you're going to split up the measurement of this path length between the proof mass and this proof mass into 3 parts. One is from this optical bench to this optical bench, one is from this optical bench to this test mass, and one is from this optical bench to this test mass. So again, the optical arrangement starts looking a little bit more complicated, but it's more for practical purposes than for conceptual purposes. The single link, the idea of measuring the separation between these two test masses, is just split up for convenience into 3 parts read by individual interferometers. So you end up with 3 interferometers on each satellite instead of 1. The detection is actually done, and this is again no different to what can be done in the lab, is done through heterodyning techniques. So you've got the incoming laser light, you've got another laser which is generating the reference signal at some reference frequency, and you're looking at the beat frequency between the reference light and the incoming light and measuring the phase of the heterodyne signal. What it turns out then is that these lasers are scheduled to operate at something like 1 micron, and instead of measuring something like a 10 picometer or 100 picometer at the laser frequency, is transformed into a 3 millimeter path length in the heterodyne frequency, in the beat node of this heterodyne frequency. So already the idea of measuring picometers becomes a lot more understandable when you realize that this is done with heterodyne techniques. Now, a gravitational wave passing through, I'm looking here at 2 satellites, 3 satellites. You've got a master satellite and 2 sort of slave satellites, and in this configuration we're looking at measuring 2 separate arms. You can measure, in principle, a gravitational wave passing across just a single baseline, a single arm length, but there are a number of complications to that. Essentially, the various noise sources coming from the laser and from the clock, this is getting into, I don't want to get really into too much detail here, but the things like the laser frequency noise and the clock noise make it essentially impossible to work with one baseline, with one arm length. But if you have 2 of these, you can essentially calibrate out these terms of the laser frequency noise and the clock noise. So this calibration of the clock noise and laser frequency noise demands 2 arms. So in this configuration, we've got 1 satellite here, 1 satellite 1 million or 5 million kilometers away, another satellite 5 million kilometers away here. And the gravitational waves, again, you can imagine are going to be propagating over this structure, and we're going to measure the separations in this arm and the separations in this arm, and that already gives you some positional, directional information at the same time. There's been quite a lot of debate about whether you should have... All right, so in principle, we can measure a gravitational wave passing across a single arm. In practice, we need 2. The question is whether you would like to have 3 arms and 6 paths. For each arm, you're sending light one way and the other way, so you've got 2 paths for each arm. And in some of the earlier D-scope designs, you've got a mother, 2 daughter satellites where these are communicating and these are communicating, but these aren't. And in the configuration that we're recommending, and has been recommended for ELISA right from the beginning, you have 3 identical satellites, and the 3 identical satellites are measuring these 3 arm lengths simultaneously. That gives advantages both for the directional information from the source. You can triangulate in this configuration better. You can measure the instantaneous polarization of the gravitational waves at the same time, and you can calibrate out these sources of clock noise and laser frequency noise. A rather curious feature of the ELISA concept, the idea is to put these satellites into an Earth trailing orbit, so that means they're actually orbiting the Sun, they're not orbiting the Earth. And Peter Bender, who was one of the originators of these ideas, also came up with a very, very clever idea for you can actually get this triangular configuration of satellites to rotate as the satellite configuration orbits the sun. So we're going to get this whole configuration to rotate in space as the thing goes around, as the whole system goes around the sun. Now, if you can get that configuration to rotate, it means that you're getting more directional information for these gravitational wave sources. You can pin down the direction better, especially for these monochromatic sources that don't change with time. Now, how on earth is that possible? And it turns out it's one of these things, there's many problems in sort of Newtonian dynamics or whatever that are quite difficult to visualize or figure out how they're going on. But what Bender formulated was that if you put these into orbits with very specific values of their eccentricity, their inclination, and their longitude of ascending nodes, then what's actually happening throughout the year is that each of these satellites is describing an elliptical orbit around the sun, which is precessing in some funny kind of way. But when you look at all three satellites together, one with respect to the other, they're actually staying in a more or less stable triangular configuration which rotates inertially as time goes on. All right. I found this very, very difficult to visualize, but I hope you've grasped the principle. You can actually get the configuration to rotate by choosing the eccentric orbits in a particular way. So what we looked into was should we recommend a configuration which has got describe it as a mother, two daughter satellites. Both my laser pointers are now dead, so I'm going to go to this physical one. Do we have a configuration where you have a mother and two daughters, or three identical links, three identical satellites? This was proposed a few years back as a way of saving money, but I think no one on our committee was convinced that if you have here you have three, you have two different types of satellite. You have this master satellite and two daughter satellites, and here you have three identical satellites. And this is the preferred recommendation now: 3 arms, 6 links, and separated by about 2 million kilometers. So our committee looked into the arm length, the number of arms, the mission duration, and the acceleration noise. And what happens is, if you increase the arm length, you increase the sensitivity, but the penalties requires more complex pointing and a higher laser power. If you can have 3 arms with 6 links compared with 2 arms with 4 links, you get improved signal to noise, improved spatial resolution, improved directionality, information on the polarization, and so on. And what we did in this committee work then is to go through, I'm sorry you won't be able to read this, but what we did was to look at the different performances of the acceleration, look at the different configurations of arm length, look at the different mission lifetimes, and then work with the data reduction teams looking at ELISA to look at the number of massive black hole binaries, compact white dwarf binaries, extreme mass ratio inspirals, and see, as a function of the different mission configurations, how many sources can be detected and what kind of signal to noise. And the numbers there are quite impressive. You know, one is looking at numbers of order 500 or 1,000 massive black hole binaries, something like a couple of thousand extreme mass ratio inspirals, and something of order 2,000 or 3,000 of the compact white dwarf binaries. Now, we went into some detail into the technology, what's available now, what needs to be brought up to speed. Missions these days all work, NASA and ELISA missions work on the concept of a technology readiness level, TRL level, and technologies are classified according to their current technology level, that is, whether it's sort of blue sky, whether it's actually been at one extreme, or whether it's been flown already on a previous space mission, in which case it has a TRL level of 8, I think it is. So we went through all the kind of technologies that were needed. We identified 4 high priority technological drivers. So amongst those, you've got certain aspects of the telescope, the power and the phase fidelity of the laser, some of the details of the optical architecture, and some of the details of the optical bench manufacture. How do you manufacture these 6 identical optical benches with very, very large numbers of components? And the idea is to do that actually in an automated fashion, so some development of automatic technology to pick up these items and place them and bond them in an automatic manner. These high priority activities that we recommended in March of last year already started at the end of last year, and they are now ongoing, and we've got a whole series of lower technology activities which are due to start up in the next year or so. So, during the committee's work, ELISA Pathfinder was launched. It was launched in 2015. ELISA Pathfinder was designed, developed as a sort of technical prototype to demonstrate the technologies required by ELISA. It ended up being quite an expensive mission, over the order of 500 million, rather than the sort of 100 million that it was originally recommended. There were 2 test masses separated by about 40 centimetres, and it's got the full drag-free control that I've described, and it's got the attitude control system as well. And the results of that, ELISA Pathfinder I think is still ongoing. I'm not quite sure what the current status of, but it was basically demonstrated all of the technologies that were required of it have been fully demonstrated. Noise characteristics extremely good, better than specification. So it demonstrates all of the components of this particular technology. It provides confidence in the picometer level interferometry, and it provides demonstration of the drag-free satellite operations necessary at the level required for ELISA. We went through scheduled planning. It sort of started, here we are in 2017. These are the showing the high priority technology development of activities, then moving into phase A, phase B, getting all the technologies up to the reference level TRL6 by 2025, and then starting the final construction, phase B, phase CD, for a launch in 2034. Just a few words on the data analysis. So all of these sources that I've talked about, the compact white dwarf binaries, the extreme mass ratio inspirals, and the black hole mergers, they are sending out signals. You've got these thousands of sources scattered over the sky, all sending out gravitational wave signals simultaneously, which are then passing over the detectors. And the question then is, how do you recognize those? How do you detect them? How do you separate them? This is part of what they do with advanced LIGO already, but the idea is that it's done by matched filtering, essentially. You start off with a signal, you predict what kind of signals should be seen, and then you go through the waveforms, the separations of all of the test masses, and pick out signals. There's an example, for example, on this is the frequency, and I think this is intensity. And then these will be signals that actually appear. You can see some of them already by eye, or some of them you can pick out by simple filtering. And the idea then is to go through them progressively, model them better, and then take their signal away from the separations that are left. So this match filtering is essentially going to require building up a massive library of all of the different effects that can be seen depending on the orientation of the source, the eccentricity, the mass ratio, and so on and so on. And this is what they're doing in preparing for LISA. These are little libraries of, I think these are extreme mass ratio inspirals, and the idea will be to detect them, to model them, to improve the filtering, and then subtract them and then move on to the next source. So it does require a sort of massive effort in modeling these sources and being able to match them in the waveforms that are seen in the eventual signal. Now, what the teams are doing is running through, they call it the mock LISA data challenge, and certain groups are simulating these perturbations of the test masses, and other groups are then looking at those perturbations and trying to extract the signals from the sources that the modelers, the simulators have put in. So as you go to progressively higher mock LISA data challenge, this was the mock LISA data challenge 1 that was run several years ago, and then mock LISA data challenge 2, they put more galactic binaries, so there's already 3 million galactic binaries. Mock LISA data challenge 4, there are 6 times 10 to the 7 galactic binaries. If you look at the massive black holes, they're up to something like modeling 4 or 6 spinning precessing black holes, a number of extreme mass ratio inspirals, and so on. And the idea is to build this up as time goes on and have more confidence that these signals can be extracted and observed. So we didn't have any particular concern that that can be done. I would say it's going to be a very, very challenging numerical or computational or simulation activity, but nothing conceptually that comes across as a showstopper. So, just to look quickly at the first detection which came out during the course of this work, on the 11th of February 2016, the first announcement of gravitational wave detection was made with advanced LIGO. They've got 2 interferometers, one in Washington State, one in Louisiana, and what you see, this is time, and this is the strain. So this is 1 times 10 to the minus 21, and this, in terms of time, it's going from 0.3 of a second up to 0.4 of a second. So this is about 0.2 of a second, 0.2 of a second. And the signal for these coalescing, this 30 mass black hole binary merger appeared and completed in something like 2 or 3/10 of a second. And the beautiful thing there, I think, is that this is the model, and this is the signal underlying it, and the period of the signal is changing, the amplitude is changing as the masses converge, and there was a perfect sort of fit between what was predicted to occur in both of these and what was actually observed in both of them. Here's the residuals. A very, very beautiful match to the waveforms that were predicted. So, one of the really interesting things is these 30 mass black holes coalescence that were detected in advanced LIGO had not really been very well predicted. I think some people believe that these intermediate black holes binaries would exist, and others didn't. But what will happen with if LISA runs as planned, then if you look at this over the whole frequency range, here's the low frequency LISA end, and here's the ground-based high frequency LIGO end, and a lot of the sources, these stellar mass black hole binary systems, will be detectable in the LISA path, in the LISA wave band. They will be followed across to higher frequencies as they spiral in, and the information from LISA will allow these signals to be predicted in the ground-based frequency range, something like a few weeks or a few months in advance of their appearance at ground-based frequencies. So one of the very powerful things, in addition to all of its other activities, is that LISA will provide this sort of indicator for this particular class of objects, of systems that are going to appear a few weeks or a few months down the line at ground-based frequencies. So while this committee was working, two main things happened. Launch and commissioning of LISA Pathfinder, which validated the release mechanism. I haven't talked about this in detail, but the thing has to be launched and then released, and drag-free control to control the two test masses. It's got very good low-performance acceleration noise, and the first detection of gravitational waves was made by Advanced LIGO, which places gravitational wave astronomy on a secure observational footing, opens the field to a broad range of scientific investigation, and in particular was detected using the same technology that is recommended for LISA. So the results of our committee's activities was that this L3 mission proposed for launch in 2034 in gravitational wave science is technically feasible. Laser interferometry between free-falling test masses provides a well-established technical baseline. We looked into the science of it, and it's a very compelling scientific case, and the technical and scientific knowledge which now resides in Europe as a result of LISA Pathfinder certainly argues for timely implementation of a gravitational wave observatory. As I said, 2034 is dictated by the funding of ESA at the moment. From a technical point of view, our committee said that you could probably launch this in 2028, so 11 or 12 years from now, if the money was available. So at the moment there is the European Consortium for LISA has submitted a formal proposal now to ESA for its organisation, for the how it will do the data analysis, how it will provide the hardware and so on, and that is currently going through a process of evaluation and should be selected. The plan is that it will be selected for study in May of this year. So that's the end of my presentation. I hope I've given you just a feeling for this complex mission, a feeling for its technical feasibility. Let me just finish by stressing a little bit the technical issues in common with Gaia. LISA requires a very accurate attitude control for this monitoring of the drag-free system, exactly at the level that we use for Gaia. So the Gaia demonstration, I think, validates that. The temperature requirement for the stability of LISA payload is around 50 microkelvin. That's roughly the same as we had for Gaia. And the structural stability requirements for LISA in terms of the individual payload is again around 10 picometers, and that was the same as the technical requirement for Gaia. Now Gaia hasn't quite met that in certain circumstances. There's some issues with the technical stability, the stability of parts of the Gaia payload, but I think with 15 years still to go, one should feel fairly confident that that is fully achievable, and it's in the spirit of a more ambitious mission that ESA wants to do in gravitational wave science. So thank you very much.
Well, thank you very much, Michael, for this very, very interesting talk. So now is the time for questions. There's one question on the back.
The wish accuracy, you can detect the positions of the sources when using ELISA.
It does depend on I mean, it depends on the type of source, and it depends on a number of things. But if I were to say something of order a few tens of arc minutes, it's something of this order. It's better than degrees and not as good as arc seconds. So something of order 10 arc minutes, something of this order. To be honest, I don't know what LIGO is. So something of that order.
Martin?
Yeah, I must admit I'm always stunned by the precision to which you can use laser interferometry, as you have pointed out, but probably it's understandable through the principle of heterodyne, as you have indicated in your talk. Now, for the sources of noise, I could imagine there is an additional factor coming in. If you imagine that, as we know, the speed of light very accurately, forget the number, but it has been measured in vacuum very accurately. There's a speed of light. Now, as we are suffering from phase shifts of a plane wavefront entering the atmosphere in optical astronomy, we can realize that in space we have the solar wind. So the presence of matter then incurs dispersion, and I was wondering whether the changing solar wind, as it passes through the 1 million or 5 million kilometer space between two in one arm, whether this makes any source of noise. Has anyone looked into this? The phase shift induced by dispersion must be relevant if you go to something like in the laser, right?
Right. I think that has been looked at. I think there has been a study done on this. I can't tell you anything more. I think we picked this up, and there has been a technical study of this.
It's a very dilute medium, admittedly, but maybe it's relevant.
Yes, I think that has been studied, and I think that is considered not an issue, but I can't give you any more details of that. I mean, again, the details of how things like, the solar wind, for example, is actually charging the test masses. So you've got all kinds of little problems there, lots and lots of little problems. The charging of the test masses, because you're actually measuring these displacements between the proof mass and the external cage electrostatically, it means you've actually got to have a fairly clever control of the potential of the surfaces and actually discharge them continuously in some kind of very accurate manner. That's done with ELISA Pathfinder already, and it will have to be done with ELISA. But it's an indication of how some of these things have to be controlled. You've got to position the center of mass of the satellite very accurately, so that there are no kind of residual gravitational gradient torques actually acting on the proof masses. When you go through this list of perturbing error sources, it's like Pedro asked me, at the end of the last lecture, what do you actually do as project scientist? Well, this is not my problem now, but the project scientists or the scientific teams, will have to go through all of there's a countless list of error sources that come in that make these measurements very, very challenging in practice. Yeah. What I wanted to tackle today was more kind of conceptual basis of the measurements.
Thank you. Sorry, thank you for the. This is on. Thank you for the talk, but I would like to address some problem related with the noise to high frequency region. I don't understand very well the noise at this region, because if you take into account the sampling what's the effect of the sampling in this kind of noise? I mean, is from a naive point of view, when you see such a noise in a given experiment, you are, yes, I'm talking about the high frequency region. Yes, because if you find this kind of noise in any experiment in physics, you expect you are undersampling your signal, no? You expect to have some signal somewhere beyond this frequency. So then, why not to increase the sampling in order to get this information? And every time you do the same experiment, you find the same noise at the same distance. So for me, the question is, what is the effect of the sampling in this?
Is not a sampling effect.
Yes.
No.
Yes, I know. But what's the effect of the sampling in such a noise?
I mean, the sampling rate for these detectors are going to be read out at a relatively low rate. It's sort of the order of a hertz, because the gravitational waves passing through, this is the frequency of the gravitational waves you're looking at. So the sampling of the interferometer baseline separation is something of the order, it's not much more than a hertz. But this is not arising, this structure is arising because of the interaction between the arm length of the satellite, the arm length separation between the two satellites, and the gravitational wavelength that passes through. If you have, you want to increase your from one point of view, you want to increase the separation between your satellite, your two satellites. Mm-hmm. If you can increase the separation between your two satellites, you get an improved ability to measure the strain, all right, because this is a fractional change in separation, and therefore if your separation is larger, then your path length that you have to measure is larger. And this is particularly important. A large separation between the satellites is important for measuring low-frequency gravitational waves. Now, if you choose, for example, if you say, right, we're going to have a 1 million kilometer baseline between our two satellites, because that allows me to measure the strain, and it allows me to measure those wavelengths, those frequencies very accurately, then gravitational waves that have a, say, 500,000 kilometer wavelength, or 100,000 kilometer wavelength, in other words, higher frequency gravitational waves, have got more waveforms in between the separations of the satellite. So you're not actually improving the measurement capability, and this comes from that process alone.
This is for me, this is a noise. Exactly, this is not the definition of a noise. This is the definition of a signal. I mean,
probably you're right. No, I take your point. I beg your pardon. This is not, you are correct, this is not a noise. This is, well, if I said noise, then this is the response curve.
Yes, okay. That's,
okay. This is the response curve. Okay. This is dominated by noise.
Okay.
This is dominated by the acceleration noise on the test mass. This is the response curve of the instrument.
Okay.
Thanks also for the talk, which is very, though the one you gave the other day, both very interesting, very appealing. So thanks very much for that. Well, my question is probably very basic. How does all that depend on the distance to the source? And I mean, is the intensity or the strain, as you call it, and the frequency of the oscillation depending on the distance and the movement of the source, or it isn't? I mean, I don't have any idea of it.
I mean, the great thing about gravitational waves is they pass basically unimpeded through the universe. So in terms of, this is why you can hope to see out to redshifts of 10, or you can see structure at very high redshifts. The frequency doesn't change. That's set.
So it's nothing like a redshift or something.
So the frequency doesn't change, but the strain will change. The amplitude will change the further you are from the source. So a nearby source would have a larger strain. Because it's as the gravitational wave is spreading out, the energy of the wave is going as the whatever it is, the cube of the distance or whatever. I think there's one point that's quite useful to stress here. Although one is talking about these apparently very, very tiny perturbations in 10 to the minus 17, 10 to the minus 18 in strain, the 10 picometer variations in the path length, the actual energy in these waves is enormous. You are basically shaking the fabric of space-time right the way across the universe. So even if you only end up perturbing it by a few picometers, the source of this is the disappearance of E equals mc squared, where m is 10 solar masses or 1,000 solar masses or whatever. So there's an enormous amount of energy in these very, very tiny gravitational wave signals.
Well, Michael, just why is 3.8 centimeter and 4.6 centimeter the relevant distances in your the experiments? Why 30? I mean, the two cubes you mentioned them. The cubes are the sizes and the distance. Why this number?
That was chosen for.
That is not nothing.
I don't think there's anything magic. It's to do with how.
Because it's very.
I mean,
it's 38.
There's nothing magical about these. It's you'd like larger masses, but everything has to be scaled up. The cage has to be bigger. No, there's nothing.
Nothing is necessary behind that.
There's no magic. I mean, this 38 centimeters becomes 5 million kilometers in the case of ELISA. And I don't know what I don't know what the test mass sizes are. I've forgotten that, whether they're the same.
Yeah, it's a very, very simple question. Just a curiosity. Where do you put the mirror to reflect the laser? In the cage or in the inertial mass?
No, it's locked to the optical bench. It's locked to the optical bench.
Okay. Yeah, that's all. Okay.
You have something like it needs to be a mirror, a telescope of the order of a meter in size to intercept enough flux from the laser. The laser is, you're shining this laser coherent beam over 5 million, whatever it is, kilometers, and then you've got something of order a 1 meter mirror to pick up the light coming from that other satellite. I mean, there's a whole in a mission like this, there's a whole host of complexities. I mean, one of the complexities is simply how you find. If you're 1 million kilometers away and the satellite shines this beam to you, how does one satellite actually find that? How do you point the satellite accurately enough to find that laser beam coming from the other? So there's huge studies done on that. How do you actually do this? And it all comes down to levels of control of the attitude of the satellite, and then a kind of sweeping motion to actually try and detect it. It's one of the arguments for not having the satellite separated by too big a distance.
Thanks, Michael, again for what I think is a wonderful, simplified talk of a very complex topic. My question is regarding data analysis. The way it is performed means that we cannot detect anything that we haven't modeled before?
No, that's not. I think not exactly. I think I don't know if people are familiar. In the old days of radio astronomy, there was something called CLEAN, algorithm called CLEAN, and what you're doing is you start off and you detect something. You see something in your signal. I mean, the idea will be to start off with the most prominent signal. Some of them, as I said, you can almost see, it's predicted that you'll be able to see those by eye. And then what you're doing is then trying to improve your modeling, sort of in a sense converging or iterating, so that for each of these big signals you get the best possible model, so that when you've subtracted it you're just left with essentially pure noise. And then you move on to the next signal. I think that's the kind of conceptual way of viewing it. So, it may well be that at a certain frequency you see a certain signal for part of the time. You may not start off with a very good model of that, but you pick out the frequency, you try and figure out what kind of source it is, and then build a model that somehow allows you to converge on. It's the same. I guess it's the same with how you work with radial velocities. In something like planet detection, you are starting off recognizing a signal, and then progressively tuning your model to actually replicate that signal. And I think it's
a synthetic interpretation. Then you have to synthesize the signal.
Yeah.
We are about to.
I want to come back to your remark just now in the discussion that gravitational waves don't know anything like extinction, and that you're probing out to redshift 10 or so. Now, how confident are the experts that we can estimate the rate of events very well? The rate of events of the kind, we have one for LIGO now, but maybe, if as you're lowering the sensitivity, or increasing the sensitivity, maybe we're swamped with many signals that people have not dreamt of.
If you look into the
field, you find 10,000 galaxies, and it's a pencil beam.
I've made a very similar points, and essentially my recommendation on this to ELISA was that we've now got. Right, let me go back to. Let me go back to this not very clear schedule, but the way ELISA missions are now. Let me just give you a little bit of a tutorial on that. It's currently found, from experience over the last few years, is that if you have prepared your mission carefully enough, and prepared your technology and got a clear technical solution. I'm not talking just about ELISA, I'm talking about any mission. Then a mission requires something like 8 years between when you start what is called phase B, phase B2, the detailed definition, and the building of the satellite. So the final detailed definition plus the building, testing, integration of the satellite take about 8 years. If you haven't prepared that correctly, it can take much longer. The great example is Bepi Colombo, which was accepted in the year 2000. The teams claimed that they could launch by 2008. We're now 2017, and Bepi Colombo still hasn't launched. All right, so I think that's a case of not doing your preparation, not getting your technologies up to speed, and so on. But the idea now in the ELISA program is that we've accepted, or ELISA has accepted the ELISA mission, but it hasn't adopted the ELISA mission. Now, my English isn't good enough to understand the difference between accepting and adopting, so perhaps yours certainly isn't. But we talk about accepting a mission now. So ELISA has been accepted, but it hasn't yet been adopted. And it will only be adopted when the technology readiness level of all the different components, so the laser, the optical bench and so on, and the sort of details of the design have been done. And the idea is that that will be adopted then in 2025 for a 2034 launch. That gives you this 8 or 9 years between here. Now, the important distinction is this is when all your money is, huge amounts of money is spent in space missions. It's the B2 CD phase. When you start getting, say, 2,000 people in industry building all the different components and integrating them. In these early phases, when you're doing the studies and so on, yes, they can be expensive. I mean, something like ELISA, Pathfinder, ELISA will probably consume something around, let us say, I don't know, 50 million euros, between now and 2025. But this is where it starts consuming 1 billion euros between here and here. So in a sense, you've got until here to get your technology in shape. And I made the same point about the data analysis, that what we need to do between here and now and here is to make sure things like the new information coming from advanced LIGO on data rates, and better simulations of the numbers and so on are done. But you're absolutely right. You can, in fact, you can write down what is the signal content of a system like this, and you can say that above a certain number of sources, that's going to be, I don't know what it is. I did this number. It's something around 500,000. All right, you start getting confusion limited, or there is not the harmonic content in there necessary for you to detect those sources. So I think you're safe up to a sort of certain level, but there would come a point where if you had too many sources, you would probably simply not be able to separate them out. Now, the question is a good one. Are we safely within this regime where we're not going to have too many sources? I think the answer is yes, but we'll have a much better knowledge in around 2025 before the mission is adopted.
So last question by Lourdes.
I would like to apologize in advance because I may have misunderstood the previous conversation with Pedro concerning CLEAN. CLEAN is based on the model of the instrumental response. If you were speaking about matched filtering, that's based on models of a library of models of the supposed to be physical underlying process. So that's quite different from CLEAN. In CLEAN, the model is the model of a point source corresponding to the instrumental response of the interferometer. Yes, that's quite different because there is no physical assumption on the processes, the source.
You're completely correct. I raised the idea of CLEAN. I think that wasn't ever. But the reason I mentioned CLEAN is that if I don't know if it's still done this way. I mean, this was done.
It is.
Okay, it's still done this way. Good, right? Well, it was done 30 years ago this way. So the idea is you look at a map in a radio source, and you can sort of go through and subtract out information. And each time you subtract out that information, as long as you know your point spread function or point response function or whatever, then you can say, right, I know that source, I take that out, and now I look what's left. And I go through that process, in a sense, iteratively. And the same, I think you can view it conceptually with this match filtering, although the process, as you say, is different. You can pick out a big signal, make sure you've modeled that, removed it, and then move on to your next signal. Thank you.
Okay. Thank you very much.